Okay, let's get started. Hopefully I'm communicating here. So today is going to be a little bit of a quicker, more straightforward lab. It's going to talk a little bit about some real-world line modeling and operation, and then giving you a sense of what's going on in terms of how a line is actually operated. So if you look at the handout, I gave you a bunch of values for a 200 meter. So we have 200 meters, or kilometers, I should say. 200 kilometers. You had R equal 0.037 ohms per kilometer. Omega L, sorry. Is equal to 0.376 ohms per kilometer. And omega C is equal to 4.518 micro, stop it. That's weird. Why is that doing that? Sorry about that, folks. I don't know why. Try that again. Omega C is equal to 4.518 microsiemens per kilometer. All right? So what we're going to try to do is going to build our equivalent pi circuit of this system. And then we're going to also look at surge impedance loading to determine when we load the line to either above or below the surge impedance loading, are we going to get the results we expect? Meaning, are we going to get some charging support for the line or for the system from the line, or is the line going to consume more VARs? And it really just has to do how much current flow is through the line, right? Because the I squared X starts to dominate and starts to consume VARs once we exceed our surge impedance loading. If you recall, the surge impedance loading is going to be determined by V squared over Z sub C, right? Now we have to be careful because Z sub C is a single phase quantity, isn't it? So if we want to make sure that this is a three-phase surge impedance load, we have to make sure that that's multiplying it by 3. And just for clarification, we'll call that V phase. Okay? So your surge impedance loading calculation is going to be based on the characteristic impedance and the expected voltage at the end of the line. So now we have to solve for an equation for Z sub C. Square root of, it's a lossless line, so we're not going to have any R. We're going to neglect any R. Square root of L over C, which just happens to be the same thing as omega L divided by omega C, right? Because the omega terms will cancel out. So these two values that you have here can be directly imported into that equation and will spit out what your characteristic impedance needs to be equal to. Once you have that, you can solve for your value of S. And keep in mind that this is a magnitude, right? It is a magnitude only. It is not going to be anything else because the Z sub C term here is just a magnitude, right? It doesn't have any real part, so it's going to be purely a Z value. It's not going to have any complex number, so it's just going to be a value of Z. Okay? So that's sort of your first step to figure out what load you'll need to have. Our second step is to come up with our two-port parameters. This is y over 2, and that is our Z value, right? So you've got your surge impedance loading from the first part. In the second part, you're actually going to see if I exceed my surge impedance loading, or if I'm lower than that, will I get some charging support? So what you need to do is you need to lay out this diagram and how it's configured actually for the line. So I have a VR equal to what? What does the lab handout say? What is it?
0.037.
What is the voltage at the receiving end?
345 kV. Divided by square root.
Isn't it 1 per unit voltage, right? So delivering 1 per unit voltage, if it's a 345 kV line, what do you think 1 per unit voltage happens to be?
345.
Very good. That is a line voltage, right? Whenever we talk about things in impedances, you have to convert to phase quantities. So you divide that by the square root of 3, and then you just pick an angle of 0 for our reference. Now we have IR. We need to solve for, we have VR. We have to solve for IR. How would you solve for IR?
You know Z, you know.
Well, we don't know Z. Right? If we want to know what the receiving end values are, we're going to use that. But again, this is a three-phase system, isn't it? So if my voltage here, what type of voltage is this, a line or a phase voltage? Very good, that's a phase voltage. If that is a phase voltage, then this here is a phase. This can be a line or a phase, but because of that, we need to multiply by 3 on the front end. Okay? So if we want to get three-phase quantities, we're going to set that equal to. So then we can solve for IR as equal to the conjugate of SR divided by 3 times VR. Yes, sir?
You said we're multiplied by 3 for our S on the receiving end because they're phase voltages?
We're using phase voltage and currents, essentially. So because those are single-phase quantities, we have to go through there. So this equation right here works for whether you're using the SIL or 0.75 the SIL. It doesn't matter. So your receiving end, in the first case, we said 75%, right? So whatever you calculate for here, multiply that by 0.75. And then you take it at an angle of the inverse cosine of 0.9. Is that a positive or a negative angle? Positive. Very good, it's positive because I said it's a lagging power factor. Who lags whom? Current lags the voltage, and when we run the conjugate of that, our S has to be higher than our P, right? So the S has to be a positive number. So now you have the information you need to solve for IR. You have your VR. We're almost ready to plug it into our matrix form, right? Mm-hmm. Except we don't know what A, B, C, D are equal to. A is equal to
D, which equals 1. Well, this is a.
This is for a medium length line.
Wasn't this large because it's 124 miles?
I think I said 200 kilometers and below will can treat it as a medium length line. If you want to use it as a long line, your parameters are just going to use hyperbolic sines and cosines.
Nope.
It'll just be a little more accurate. If you use medium length ones, it would be fine because that's right at the cusp.
Is that ZY divided by 2 or is
ZY over 2, yep. RB is equal to Z. RC is equal to Y times 1 plus Z over 2 times Y over 2, and our D is the same as RA. Now, we have the ABCD parameters, but they're written in terms of the entire length of line. So these values that we have here, right? Those are per kilometer lengths. So to be able to calculate those, you need to multiply all these by the length of the line. GTH, right?
to actually get the ohms?
To actually get what the ohms are. We don't want ohms per kilometer. We want ohms per mile. Okay? So when you do that, your Z value is really just going to be R plus J omega L times 200. Your Y value is going to be equal to omega C. What do we do with our omega C? Just have to multiply it by 200, right? Right? because it's Siemens per kilometer. So if you just multiply by the kilometers, you get the actual Siemens. Don't forget, though, I need my Y over 2 on each side. So I need to divvy that up in half.
What do we do with the micro Siemens? Should we be, keep,
It's just times 10 to the minus 6.
but I mean, keep the unit?
You have to, yeah.
You don't have anything avoid it? Like,
If you keep micro, you
have to
won't.
use that.
You have to use the micro, yep.
That's what I'm saying, inside, right?
Pardon?
Just as long as micro needs to be included within the measurement.
Micro needs to be included. So now you have enough to do the model. You can spit out your VS and IS. The question is, how do you know if you're right? Well, remember we said if our load power, right? So if the load, we'll call it S, is greater than the SIL, then the line consumes bars, right? If the load S is less than the SIL, then the line supplies bars, right? That's essentially what we talked about in the previous couple classes. How do you know if your line is consuming bars or supplying bars?
Find the cell.
You have to find the SIL.
See if you're more or less power.
Pardon?
See if you're more or less than the cell.
See if you're more or less in the SIL, but how do you know if you're, how are we confirming that?
This side.
The easiest way, or one of the easiest ways, is to solve for Q at the sending end, and then Q at the receiving end, and see which is bigger, right? If the load is bigger than the sending end, then I should have this. If the load, so this corresponds to this one, and if QS is less than QR, then you have this case. So you just have to calculate the Qs. All right? How do you do that? Well, we have a sending end is equal to either 3 or square root of 3. I would just use your 3. VSIS conjugate. Your receiving end is 3 VRIR conjugate. Pull the Q out of those, and you can do that. The other option is, what is the power factor at the sending end, and what is the power factor at the receiving end? Right? And then compare those, and then you can make a determination if power is being supported or not. Okay? I'm going to try something with MATLAB. I have no guarantee this is going to work. It's really glitchy, but let's give it a try. So we're going to go to MathWorks. You can use a web browser. I just don't know if the app will run. It didn't work the other day.
I've used the MATLAB app on iPad a couple times and it works. But
Yeah, but it doesn't always work in Explain Everything. So here's my drive. Nope,
right, I guess you could.
it doesn't work. So it doesn't work, sorry. It should launch in here and bring up the file. So for those of you who are in TV land watching this after the fact, you'll have to see the work independently. I do have a script file that kind of walks through that first part of the process that I would have to sign off because I can't bring in a MATLAB. Well, I'll bring in my script file, so let's do that. I'll bring in a script file, and I'll bring it into Google Drive. No, it won't come up. I don't know why it won't come up. It's just a .m file, but it will not launch it. It's giving you the
You
big.
need to open MATLAB first and then
But that's what I'm saying. I can't open MATLAB from this app, so I can't do it. Sorry, so it will not work through MATLAB. If I can get it to work, maybe what I'll do is I'll just import it as a Word file or in a notepad and then bring it through that way. So let me pause this. So I'm going to pause. All right, let me try that again and see if I can paste it here. No. Well, that didn't work. Let me try that. Okay, let's try that again. How do you paste into here? And
Tap again, and it should.
tap.
Yes, hold again like you did to copy the text, it should come up with a paste.
Okay, so that's from the script file. Thank you. You guys are word geniuses. Yeah. So essentially I did a couple things. I tried it depending upon if I wanted to just see if it changed my results by using resistance or not. So I just had this multiplier 1 or 0, essentially, if the resistance is that or not. And then here's my XL and my YC. Those are just inverted, so I multiplied them out. I solved for Z and Y, as we talked about. Then I got my characteristic calculation, square root of XL over YC, right, or WC, it's the same thing. And the reason why it's the same thing, because remember, for a capacitor, the impedance, X sub C, is 1 over omega C, right? That's the reactance. But Y is equal to 1 over WXC, which is just WC. So that's why it ends up being the same term. So here's my voltage. Here's my calculation for my receiving end. And then I just did the 75% value for my receiving end power. And then I just called it my 75%, right, my 0.75, and I just added on to the label. That EXP J to the whatever is, again, the only way in MATLAB that I know of to enter in complex numbers. For those of you in ECE, is there a better way to enter in MATLAB complex numbers? I don't know if Dwayne taught you something sneaky, but it works fine with this, but sometimes it trips people out. What's that?
So Dwayne just is sneaky.
Did it sneaky as well? Okay. You can always write a script, but then that gets more confusing unless you know how to write scripts. Then I calculate R, exactly what IR, just what I've talked about in this lab, right? It's S divided by 3 times VR, right? And I took the conjugate of that term. Then I just added this display IR. Whenever you see a disp in my code, this is what I've just gotten familiar. It means I'm going to try to display something. And it doesn't mean I'm actually going to display it on the screen. I might just display it for me to look at absolute value quantities and whatnot. So I look at magnitude and angles, and that's what that vector gets set up. Then I build my ABCD, and then I solve for my sending end values. Then I just pull out V and I, right, out of the matrices. I just assign them. And then all I'm doing over here now is I'm calculating the theta differences, right? So I'm looking at my theta S and my theta R. So I could do power factor calculations, right? If I take the cosine of this, right, that's going to give me the power factor at the sending end. If I take the cosine of this, that's going to give me the power factor at the receiving end. And then I can go ahead and see which one is greater or lower, depending on the condition. I also did this one here. So that's one way to do it. The other way that I did it is this step, here, which is I actually calculated the sending end power, the S. I pulled out the Q from the sending end. From the receiving end, I just grabbed this value here, right? I just pulled it from that value. And then I looked at the difference between the two. And in the case of the 75%, this difference is a negative number, right? Is that correct? Again, I would run MATLAB if this app would allow me to run, but it does not. As you see, I wouldn't link through my next step. Well, In the case of the power being demanded at 75% of the sill, should the line be supplying bars or absorbing and consuming bars? What is it? If the power demanded from the load is less than the sill, the line should be supplying bars because the current through the line is below that break-even point when reactive power support is provided by the capacitance to ground. So the line should be supplying its own bars, which means this number should be negative because there are less Q put in than taken out, right? The QR is greater than the QS. So if I've got a line here, right? I've got some Q in and some Q out. Q out is greater than Q in. I have to put additional reactive power someplace else, right? That's from the line. And it only applies because in this case, we have a lower value of loading than the sill. Okay? Is this helpful? Give you enough to get started? You pretty much have the first part of the lab done, which will also help you on the homework perhaps. So take a look. I'll stop recording at this point. Unless you have any questions, I can always start back up again if necessary. That's the nice thing about this. Does anybody want me to leave this up? Do you want me to erase some of these things? Actually, I know what I can do. That doesn't work anymore. How's that? You all are going to make me an Apple Pro before you know it. Okay, I will stop and keep this clear. Good luck.